Hi folks, it's Mr. Moodlage here with the video for MPM2D. This time we're looking at some representative questions for studying for Module 1, which is a module on linear relations. So here I have 5 representative questions, and we will go through them each full detailed walkthrough. So one question right here, this is an example of analytic geometry number 1, part of that, which is AG1, we can say it's about equations of lines. So here the question is saying determine the equation of a line passing through the points. We have one set of points there, and then we have another point right here. So when you get a question like this, it's a very good idea just to draw a little chart, like a t-table, x and y, right? And then you can go ahead and, right, this is your first point, the x and the y. So you can just put them here, 5, -6. And the second point is right here. It's like the second x and second y, right? New point. So you can go -10 and 9. And now you just want to find the difference in the y, the change in y. So to go from -6 to 9, I have to go, so 9 minus -6, so that's 15. I have to increase by 15, right? And it's always good practice, folks, when you're doing these, just to use your calculator to check. But in this case, that's okay. So I would do 9 minus -6, and I would get 15, right? Yes, okay, very good. And also here, in the x direction, so in the change in x, I'm going, how do I go from 5 to -10? Well, it's actually a decrease of 15, right? That comes from -10, my final, minus 5. So -15 there, and you can check that as well. Now, we call this the change in my y. This is the change in my x. Well, to find the slope is just rise over run, right? We know this, or the change in my y. So delta y over delta x. That's a shorthand way of writing change in, that delta right there. But long story short, it's just this positive 15 divided by this negative 15 right here, right? And so that gives me a -1, because positive divided by negative is a negative. So I have my slope there. This is my m value. Now, in order to come up with an equation, I need 2 things, right? So at the end of the day, my equation is going to look like y equals mx plus b. I just found half of the missing puzzle. I need to figure out what m and b are, and then I have my equation. I just figured out one piece of that. So I know what m is now, -1. So if I take this, move it up here, I need to find b now. And the trick to doing this, so once you find m, that's your step 1, to find b, you're just going to make use of any point that you have, either this point or this point. You could pick whichever one. I'll go ahead with this one. And you're just going to replace the x and the y with these coordinates right here, respectively. So x is going to be 5. So right here, that's going to be 5, and then the y is going to be -6. And so everything else stays the same, -1 plus b. Now let me just simplify this a little bit. So -6 is equal to -1 times 5 is -1. Sorry, -5. -1 times 5 is -5, plus b. Now what I'm trying to do here is I'm trying to solve for b. So for me to solve for b here, I'm going to add 5 to both sides. I want to get rid of that -5 on the right side. So add 5 to both sides. So this becomes -1 is equal to b. So now I have my answer. Y is equal to -1x, or just -x, same thing, -1. That is the answer that to this question right here. Okay, so 2 steps here when you're trying to answer these questions. First step, find your slope, find the value of m, doing this, and then find b by using that updated equation, right? Y equals mx plus b. You find m from step 1, write that in here like we did here, and then use a point from your question. You can use any one. They should both work. They will both work, so use any one. I used this one. And then plug that into x here, and then y here, and just solve for b. and write your final answer that way. Okay, so that's one question. All right, moving on. Another part of linear relations is looking at a second part here. So analytic geometry, second part of this, AG2, is looking at solving linear systems graphically. So this is a representative question for that, right? I tell you here that a system of three linear equations. So I'm stepping the, the level here a little bit, but instead of two, it's just three linear equations, only has a solution if all three lines intersect at the same point. So I tell you this, it's a statement. I say that three lines have a solution if all three intersect at the same point. Now, here, I'm giving you the equation of three lines. So consider the following system right here. So we have, the system is made up of three equations, 1, 2, and 3. The first two are shown in the graph. So I graph the first two for you. So that's this one and this one. Notice that this one is actually in not even in y equals mx plus b form. But if I wanted to do that, right, I'd add x here, I'd add x here, and then I'd get something like 2y is equal to x plus 8. And then I divide both sides by 2, right? Divide by 2, divide each of these by 2. And then I'd get something like y is equal to half x, or x divided by 2, same thing, plus 4. So I'd get something like this. And now I can realize that, yes, in fact, this right here is the equation for this line right here, because see, my y-intercept is -3, and my slope is 4 over that invisible 1, meaning that from here, that starting point, I go up 4, 1, 2, 3, 4, and move one to the right. I go up 4, 1, 2, 3, 4, one to the right. That's kind of how I get the dots to make this line. Now for this one, once I've written it in this format, I could see, well, I start at plus 4. That's that plus 4, the y-intercept, the b value. And then I'm going 1 and 2 to the right. 1, 2 to the right, because my rise is 1 and my run is 2. So that works. And a preliminary question, even before reading the rest of the question, could be like, well, state or tell me, just by looking at this, what is the point of intersection? What is the solution of just these two lines? Well, that would just literally be telling me the coordinates of that point. So these two lines, so I could say something like lines, let's say this is line 1, and let's say this is line 2. Okay, so I could say lines 1 and 2 have the solution. So just looking at lines 1 and 2, they have the solution given by, what is the x-coordinate of that point of intersection? 2, 5, right? X is equal to 2, y is equal to 5. This is how we kind of solve problems graphically, right? Using graphs. So good. Visually, I've solved that. And now I have a third line here, which looks like that. And it's asking me, does this system of equations, all three of these lines, do they actually intersect at this point? Well, really, the easiest way to do this is literally to go ahead and graph this. The y-intercept is 2, so put a dot at 2, and then make use of the rise over run. So I go up 3, because the rise is 3, 1, 2, 3, and then I go over to the, so run of 2, so to the right 2, 1, 2, and put a dot right there. So starting right here, right? So I end up right here. And look at that. I could keep going, but really 2 points is enough. I can also go backwards here too. Like if it's up 3, right 2, I can go down 3, left 2 as well to kind of get that, more points there. But at the end of the day, if I connected those points, let's just make this a little bit cleaner here. If I graphed those points, connected those dots there, I would get a line like this. And this line, so let's call that line number 3, actually goes through that point of intersection as well. So the answer to this question, does this system of equations have a solution? It's yes. And the explanation to this is all three lines have the same point of intersection, or POI for short. that's it. So when I graphed the third line, it went through that the solution for the 2 lines as well. So it went through that point 2, 5. And that point of intersection, I could say, is 2, comma 5. Okay, so that's how we kind of do that problem. Okay, let's take a look here. Keep moving on here. I have another, type of representative problem here. This one is looking at more parallel, so a third component of linear relations, which is parallel and perpendicular lines. I'm just noticing here that the numbering is weird. Just ignore that. So this should be like the third part. This should be the second part. And that one was the first one. So that's okay. We'll just edit the numbers as we get them, but that's just a generic numbering. But yes, this is the third of a sequence of 5, I guess. So third, component of analytic geometry could be on parallel and perpendicular lines. Here, a question could be, a very good question is, determine the equation of a line perpendicular to a given line passing through a point like this, right? So how we do these problems is always start with the given equation, right? So start with y equals 1 over 5x plus 3. Now the question you have to ask yourself is, this line, okay, well, it looks like something, sure. How do I get the perpendicular? So the line that's perpendicular to this, what is the slope of that, right? So first thing you have to ask yourself is, what's the slope of this line? Well, the slope, m, is just going to be 1 over 5, right? It's literally this number right here in front of the x, the coefficient of x. Now you have to ask yourself is, what is m perpendicular? Well, this is what you have to remember. You have to do, so it's the negative reciprocal. So you can't just flip it, but you have to take the negative of that. So change the sign. Here it's a positive, right? So it becomes negative 5 over 1, or just negative 5. So that's the actual slope of my line, the perpendicular line. Now, once you figured that out, this just becomes like the first problem, finding the equation through a line, or finding equations of lines, right? Because I have a slope and I have a point. I want to now figure out the equation. Will always revert back to y equals mx plus b. I just figured out the slope of my new line. It's going to be negative 5. Now I just need to figure out this b right here. So in order to do that, I have a point right here. Use that point. Remember, this is an x, a given x on my line, a given y. So sub those values into x and y here. So into x, I'm going to put 1, and into y, I'm going to put negative 7. And then just fill everything else here and solve for b. So this is going to be negative 7 is equal to negative 5 times 1 is negative 5 plus b. If I, remove the negative 5 from the left, from the right side, I have to add 5, and I get negative 2 is equal to b. So when I update my equation, because I'm trying to find the equation, I would say, therefore, y is equal to negative 5x minus 2. So this line right here is perpendicular. So going back to the question, this equation of this line that I found is perpendicular to this line, and it goes through this point. So very nice. All right, we're getting to the fourth component of linear relations, which is looking at solving linear systems by comparison. So in a nutshell, this is just looking at, can you find the point of intersection of lines, such as this question right here. So I have 2 lines right here, y equals 5x plus 3, and y equals negative 2 over 3x plus 16. I'm trying to figure out the point of intersection here. All right, so here we set the lines equal to each other. So that's our step 1. So I'm literally going to say, okay, well, 5x plus 3 is equal to negative 2 over 3x plus 16, right? I can do this because both lines are written y equals something and y equals something. We know at the point of intersection, both y's have to be the same. So this y, that the y coordinate when they're the same, are going to be the same when they cross, when they intersect. So this value, 5x plus 3, has to equal this value, negative 2 over 3x plus 16. And I'm trying to figure out what the x coordinate is here in doing so. So here, when I get to this situation, I want to get all the x's on one side and all the numbers on the other. So I'm going to add 2 over 3x here to both sides to eliminate it from the right side. So I get something like this. And at the same time, I'm also going to, actually, let me just write it out first. So 5 plus 2 over 3x plus 3 is equal to, well, this just disappears, and I get 16 on the right side. Good. Now on the left side, I want to get rid of this 3 right here, so I'm going to subtract 3 from both sides. So I get 5x plus 2 over 3x is equal to 16 minus 3 is 13. And now, in order for me to, simplify that, combine those two like terms, because they're both x terms, I'm just going to realize that this denominator of the 5 is a 1. And in order to add fractions of any kind, add, subtract, I need to have common denominators. So here, I'm going to multiply by 3 and multiply by 3 on both the numerator and the denominator. And I'm going to get 15 over 3x plus 2 over 3x is equal to 13. Now I can add the two fractions. So this is going to be 17 over 3x is equal to 13. And now when I get to this stage, I want to get rid of this 17 over 3. I want to make that 1, right? So I'm going to divide both sides by 17 over 3. Divide both sides by 17 over 3, right? So then 17 over 3 divided by 17 over 3 is a big 1. So I get x on the left side, and 13 divided by 17 over 3 is the same thing as 13 times 3 over 17. So at the end of the day, my x value becomes 39 over 17. Not a pretty number, but that's, when we're dealing with fractions, that happens quite often, right? So I have an x value. Now, when you get to here, realize that you're not done the question, right? This is just half the puzzle. For point of intersection, remember, I need an x and a y. So I just found half my solution here. Now what I want to do is take this x and plug it back into either this or this, whichever one you like. I would pick the easier one. So like this one, for example, because there's no fractions, there's no negative signs. So then you're just going to write y equals 5. And into x, you're plugging in this answer that you got, 39 over 17, and plus 3. So that's going to give you the y coordinate at that point of intersection. So then when you multiply fractions, right, you just multiply the numerators and you multiply the denominators. So here, like the 5 has a denominator of 1. That's okay. So 5 times 39 is, do this on the calculator, 195, and then over 17. That does not get reduced in any way, so that's okay. And then plus 3, right? So then here, this fraction has a denominator of 1, and I times it by 17, times it by 17 to get that common denominator. So 17 over 195 plus that is going to be 51 over 17. Again, you have access to a calculator, so you want to make use of this. 51. So this is 246 over 17. And that itself, I believe, is not does not reduce anymore. So that's my y as well. It's not a pretty fraction, not a pretty number, but still works out. And at the end of the day, I just found my point of intersection, POI, is equal to 39 over 17, comma, 246 over 17. So folks, I hope you can understand another thing here is if we put this in our calculator, 39 divided by 17, we would have gotten like 2.29 and then a lot of decimals. But if I gave the answer for x is 2.29 and I did all this math using that, like right here, I would have not gotten 246 over 17. I would have gotten a different answer. It would have been close, but that's why we like fractions for working with this stuff, because it actually gives us an exact answer. So this is exact. And then once I get here, I can kind of round if I want, but just keep that in mind, okay? If you do want to use decimals, then you want to have at least like 4 decimals. So that way when you kind of round and stuff like that, it won't affect future calculations like we have here, okay? All right, so we got the answer to that. And just one more question here to go. This is relating to the last part of linear relations for this module. And this is looking at a 5th component, which is looking at the number of solutions in linear systems, right? So we're looking at specifically the number and then of two equations and being able to justify this, right? So it looks complicated, but in reality, it's not that bad at all. Like when we do 3 examples here, you're gonna see it's very straightforward. So, and you already know this, believe it or not, right? If you've watched this video this far, then this should make sense. So I'll just make 3 columns here to make it even more, to show the difference between the 3. So all it's saying is this question is state the number of solutions of each system of equations, justify your answers, right? So take a look at this one right here. So I have 2 equations. Y is equal to 2 over 3x plus 6, and y is equal to negative 2x plus 5. So these 2 equations are literally 2 different equations, right? Notice that m of equation, like m, we have 2 different m's, right? The 2 over 3 and the negative 2. So these 2 m values are not the same, so they're not parallel, and they're not negative reciprocals of one another. So they're not perpendicular either. And even more, the y-intercepts are different. So these 2 lines are literally like, if you think of a sketch, these are just like, okay, one goes like this, one goes like that, and the other one, so that's like, yeah, positive 6 and up to right 3, up to right 3. And the other one is like starting at 5 here, just below that, and then it's down to 1 right, down to 1 right. So like that, right? Even steeper, but like that, right? The important thing is to note that this is just one point of intersection. So when the 2 lines have different slopes and, different y-intercepts, or just different slopes in general, then you're gonna get just one point of intersection. So this right here, I would say, has one solution. One solution, one point of intersection, because, so that's my short form for because, B slash C. So because they intersect at one point, or because the slopes are different, the slopes are different. So whenever the slopes are different, it's fair to say that there's just going to be one solution, right? Even if the slopes are negative reciprocals of one another, there will just be one solution. Okay, now here, this is an interesting case right here. So here, the slopes are the same. Okay, so if you take a look at this first equation, 5x minus 3 over 2. So even without drawing a graph here, what is negative 3 over 2 as a decimal? That is literally like this equation, the first one, if I rewrote that, that would be 5x minus 1.5. What do you notice about this equation that I just drew, that I just wrote in decimal form, and this equation right here? They're the exact same. So when I have 2 equations that are the exact same, they just lie on top of one another. So this would be as like a, negative 1.5 is, let's say, roughly there. Again, I'm not drawing this to scale at all, but I'm just sketching this. So negative 1.5 is like, imagine somewhere there. And then 5x would be something like that. So literally that's 5x minus 1.5, y is equal to, and then the second one would just literally be the exact same thing. So on top of that. So this is an example of something where we have infinite solutions. So has infinite solutions. And the reason for this is because the slopes and the y-intercepts, y-ints, are the same. In essence, this is linear, so in essence, the 2 equations are the same, i.e. 2 equations, that's my short form hand way of writing equations, are the same. Are the same, exact same, not just somewhat, but exact same. Okay, so that's why there's like just one or infinite solutions here. So the answer to this is infinite solutions. This one has one solution. All right, let's take a look at, we saw this one right here. We saw one where there was infinite solutions. There is one other type of scenario, right? Take a look at this one. So I have y is equal to 3 over 2x plus 10, and y is equal to 1.5x plus minus 8, rather. minus 8. So this first equation, if I wanted to, work with all decimals, work with all fractions, but don't just, sometimes that's where it gets confusing when you're working with fractions and decimals. So here I'll just convert this to a decimal because 3 over 2 I know is nicely just 1.5, right? It's 1.5, so 1.5x plus 10. Okay, that's the first equation. This is the second one. Okay, what do you notice about these two now? Well, first of all, they're not the exact same. The m's are the same, the slopes are the same, and the y-intercepts are different. So when the slopes are the same and the y-intercepts are different, what type of lines are these? Think to yourself, right? The slopes are the same, which means that, and they start at different points. Well, the only scenario for this is if we wanted to draw a little sketch here. Well, one of them could be starting at plus 10 here, and I'm, 1.5 means I'm going 3 up, 2 to the right, so roughly something like that. And the other one is going to start at minus 8, so let's say somewhere over here, and it's literally going to be the same slope. It's literally going to be just the exact same slope. So if I copied this correctly, let's see, paste it here. It's not really allowing me. That's okay. Let's cut it. Okay, there we go. Let's paste it now and see. I think it's pasting in the wrong place, but that's okay. So I can literally draw something that's parallel just exactly to that. So these two would be parallel, never going to cross. And I hope you could see that this is an example of something that has no solutions because they're never going to cross. So this right here has no solutions. And the reason for this is because the slopes are the same and the y-intercepts are different, right? If the y-intercepts were also the same and the slopes were also the same, they would be like this case right here, number 2. They would have infinite solutions. So as long as you have the same slope and different y-intercepts, it's always going to be parallel. So these are 2 parallel lines. Okay, there you go. That's really the crux of all of this. That's brings it all down, makes it all come together. I hope that was helpful. You should have a good, solid understanding of linear relations now. All right, good luck, and thank you for following along.